We have here Dr. Subhash Saha from University of Technology, Sydney, Australia. Dr. Subhash Saha presently working at University of Technology, Sydney, Australia as a senior lecturer of mechanical engineering. He has also worked as a postdoctoral research fellow for more than 6 years at School of Chemistry, Physics and Mechanical Engineering of Queensland University of Technology, Brisbane, Australia. Dr. Saha received his PhD in computational fluid dynamics applications to heat transfer in buildings from the School of Engineering and Physical Science of James Cook University, Australia in 2009. His current research interests are thermal studies using phase change materials, solar thermal technology, natural convection, heat transfer in buildings, and then other confined geometries, scale analysis for the transition flow, computational biomechanical engineering, etc. Dr. Saha has more than 200 publications, including 120 journal papers, mostly published in high-impact journals. Total citation of Dr. Saha is 1720 with H index of 21. He has more than $1.4 million funding, including 2 Australian Research Council linkage grant, 1 Australia-India Strategic Research Fund by Australia Academy of Science, and is involved in 2 National Nature Science Foundation of China and NSFC funding. So now I'd like to invite Dr. Saha to present his session on modeling of thermal energy storage using phase change materials.
Thank you, Dr. Roy. And good afternoon from Australia and good morning in Malaysia, I think. Thank you, Dr. Roy, for introducing me. And I found that he knows all my data very well. Today I would like to talk about mainly the computational fluid dynamics application to phase change materials. But because it is a workshop, so I would like to talk about a little bit about the phase change material and what is it and what is the importance of this phase change material for energy storage. So as you know that the energy usage at home is mostly heating and cooling. So in Australia, we mostly use solely for cooling because it's a bit hot in Australia, especially the north part of Australia. But in Sydney and Melbourne, we have a little bit of cold. And so about 40% of our everyday energy uses. And we also use this energy for water heating, about 23%. And some other appliances, for example, television, computers, and some other gadgets. And also the freezers, about 8%. And lightings, cookings, and some we waste is called standby power or some ghost power. So this is our everyday life. We use the energy. And in 2016, the total Australian energy consumption, we can see that the renewables energy is only 70%. And the fossil fuels, we use 83%. But in Australia, we have a lot of resources, for example, the solar energy, the wind power energy. We can easily increase the uses of renewable energy. So we have some plan. I'll talk about this one a little bit later. But in 2016, it was very low, only 70%. And this one is 2017. We increase a little bit, is about 20.3% of using renewable energy. So what happened is the New South Wales climate change policy, the framework sets out the aspirational long-term objective for New South Wales to achieve net zero emission by 2050. So that is our target. We plan. All right. So we want to use our natural resources. For example, the solar power or wind power. We don't want to use the fossil fuel. And the way Greater Sydney's urban structure and build from develops over time can support this New South Wales transition towards net zero emissions. However, this target all right, so it's very interesting that Sydney is actually very closer to being a zero carbon city than you think. So what we thought 2050, I think we can reach there before that. All right. So if we use the available renewable energies resources in Sydney region, we do not need any fossil resources anymore. And it's a very interesting statistics is released very recently that the energy we use in total Sydney area is coming from renewable energy. How is that? So almost every house in Sydney, we have that solar panel, and that actually producing a lot of electricity. So during the day, we spend the electricity we need, and the rest we supply to some other states or somewhere. And we have to get back that at night. We have to buy from the power industry. But the total amount of electricity we need in Sydney, actually we are producing in the day. So the main challenge is how to store this energy. So our current system, we cannot store. We can produce or we can use it. Or rest of the energy we can transfer to other states or other places. But if we could store this energy, then we could use this on at night time, or like some rainy day, or when there is no solar energy available, that time we can use it. So that's a big challenge. So we think that the energy storage, thermal energy storage, we believe the battery is the main source, but battery cannot solve the world's biggest energy storage problem. Because fluctuating solar and wind power requires a lot of energy storage, and lithium-ion batteries seem like the obvious choice, but they are far too expensive to play a major role. This is very, very expensive. We can't afford it. So therefore, the challenge remains in understanding energy storage as an investment. So there are other sorts of energy storage, which is called thermal storage is water. We can use the molten salts or some other fluids. So what we can do in water, we can heat the water during the day, and we can make some, like under the ground, we can make some reservoir. We can put the hot water there in the daytime, and nighttime we can take it out and use our to like at nighttime use. There are some compressed air. What we can do is we can use the daytime electricity or some excess electricity to compress the air, and this compressed air together with some natural gases, we can use this one for turbine to create energy, to create electricity at night time. So this is another way. We can also use for hydrogen production. So that hydrogen can later on can produce electricity. Then we can also use some flywheels and some other stuff. So until now, what we found is the phase change material, which is called PCM, is a nice way to preserve the energy. So, what is the theoretical appeal of phase material? Well, it gives extra thermal mass effect, and also it is relatively lightweight, so it's easy to use it, easy to carry. So that's the theory. Now the question is, what is the benefit of thermal mass? So at first I would like to talk about the replacing of thermal mass, and then I would like to show its effect or its benefit, and then we want to correlate to the phase materials. Okay. So the thermal mass actually slows down the response to change in temperature. So if we apply the heat to the material, it increases its temperature. Okay, so if you heat the material, it increases the temperature. So if you take heat out of the materials, it goes down its temperature. So just opposite. All right. So you can heat it or you can take the heat out from here. So in both cases, either it will increase the temperature or it will decrease the temperature. For example, in the case of water, increase the temperature is actually proportional to the heat we apply. So take the same amount of air, that is 1 kg of air, you will get a different response. It's a different response because that material responds differently in the heat. So in the case of water, 4.2 kilojoule of heat added will change the temperature by 1 degree Celsius. Whereas for air, you will need only 1 kilojoule of heat energy to change the temperature by 1 degree Celsius. So that makes actually several points about materials and heat. For example, if you look at the line in the case of water having a low slope, so you see the slope compared to the air, it's a low slope. The lower the slope in the chart actually corresponds to the higher the thermal mass. So in other words, the more heat you need to add to get a certain amount of change in temperature, that's what the thermal mass is all about. All right? Because at the end, we need to extend. We extend how long the material can store the energy. So in physics and engineering terms, so this is called the sensible heat. In other words, the change in temperature is directly proportional to the amount of heat we apply. So what is sensible heat? Sensible heat is you are applying some heat and the material increase its temperature without changing its phase. The phase is not changing. If it is solid, it is solid. If it is liquid, it is liquid. It is not changing its phase. All right. So that is in particularly characterize the materials that actually slope, the characteristics of the materials, because the specific heat of materials, for example, in case of water, so 4.2 kg per degree of change per kilogram of materials. Now, So that is the way we characterizing materials in terms of its response to heat, either added or removed. Now let's think about that in terms of sudden change of temperature. So this blue line, as you can see, the blue line represents the change outside temperature, for example, in a building. So the outside temperature is this blue line. So suddenly change from 0 to 100 degrees Celsius. For example, it is not real. All right. So the outside temperature of this one, and the red line represents the inside temperature in response to the outside temperature. So this is totally a hypothetical step change in temperature, which is not realistic. I just showing you how we get the response. But it makes the point that you get sort of curve response, like the characteristic asymptote up to the final temperature. As you can see, so initially for a small amount of time, so this red line increases and then increases further because the outside temperature remains the constant and it's getting time to get the similar temperature stop. And you can see after certain times about maybe 50 seconds or 50 minutes or sometimes is getting the similar temperature at the outside. So you see this curve, the response curve is not exactly the same as the outside temperature. So it totally depends on the material properties, how the material responds. So in this curve, you can see more realistic cases. For example, this blue line is initially the constant and this increase linearly and then stay there for some time and then it's coming down. We can compare this one with our daily diurnal temperature. You can, if you can consider, for example, in the morning when we see the sun, so the temperature increase linearly, and about 11 or 12 o'clock, maybe 11 o'clock to about 2 or 3 o'clock, the temperature almost remains the same. And after that, in the afternoon, the temperature decrease. All right, and that's very minimum temperature at night time. So this is the outside response in a building. And if we have like here, we have the red line or red curve is a low thermal mass, and the yellow one is the medium thermal mass, and the green one is the high thermal mass. You can see the low thermal mass responds quickly, and the high thermal mass responds very slowly. So the thermal mass and the insulation. So people have some misconception about this thermal mass and the insulation, because they think that the high thermal mass is actually insulating. That's not right. And also the insulation doesn't help slow down thermal response. That's also not true. But people they think about it. The reality is the thermal response time of a function of mass times the insulation. So this is the product. The thermal response is the product of mass and the insulation. All right. So that means if you want to use this low or high thermal mass product as a facial material in your building, you can also use the insulation as well. So that both can give you good thermal response. All right. So that means the doubling insulation and doubling mass have the same impact. That means they give you the same proportion, all right, to the response time. So the thermal mass benefit mostly when you have high diurnal temperature variation. If the variation is not high, if it is like a constant, you can't get benefit from this thermal mass. Okay, you should have like some variation, and that's very good in contrast to Australia. So we have our temperature difference in a day is about 15 to 20 degrees Celsius. So that's is a very effective using in Australia. And I also think that is also benefiting some Asian countries. And the average temperature within the comfort zone. So if the average temperature from the fluctuating temperature, if the average temperature is in your within your comfort zone, the temperature you want at home, so then it is more effective. So its thermal mass average out the inside temperature. So do you think the thermal mass always good? Actually no. For example, if it starts from very cold, all right, for example in Melbourne, or maybe in New South Wales in Blue Mountain, sometimes you can see some ice. So in that place, it is not possible because it takes longer time in the morning to heat up. All right, so it takes longer time, so it is not very useful. Okay, so it takes a lot of time and energy to get comfortable. And if it is very hot, like the heat wave, the thermal buffering actually overwhelm is not also very good. All right, so thermal mass is not always good. Now we just come back to the phase change. So what is phase change? The phase change actually the melting or freezing. This is actually phase change. So meltings and freezing, so just the opposite. All right, so melting is from solid to liquid, and from liquid to the solid is called the freezing, or evaporating or condensing. All right, there is also a phase change. So to change this phase, it involves the latent heat. All right, so the very good example of this phase change material we everyday use, that is the water. Okay, so water, we have the melting points or the freezing points is 0 degrees Celsius, and the boiling or some condensation is 100 degrees Celsius. So what happens is, if you have some ice which has -4 or -5 degrees Celsius, if you put that on to somewhere and increase the temperature, what happened? Initially, using the sensible heat, it increased the temperature up to 0. And after that, temperature doesn't change until the whole ice melted. All right, and then when all the ice melted, then start the temperature rise until 100 degrees Celsius. So when this water becomes 100 degrees Celsius, then it start boiling. All right, and then stop changing the temperature until all the waters evaporate. All right, so that is some sort of how this phase change material works. So if you see here, in terms of ice or water, I can give you some overview here in terms of a curve. So initially, as I said before, if we put a -5 or -10 degrees Celsius of ice, and if we heat it, if we apply some heat, its temperature start rising up to here, and then if we and then it's become 0 degrees Celsius. So here the ice becomes 0 degrees Celsius, and then again we are heating, and we expect the temperature should go this way, but it doesn't, because it's changing the phase. It's changing the phase from solid to liquid. and we are hitting, keep hitting, and then all the solid materials melted here, and then it becomes water, and this water temperature start rising. So that is called, so from here to there is called the latent heat. Okay, so this is called the latent heat, and this is called the phase change temperature. Okay, the phase change temperature is this. So for ice, this latent heat is 334 kilojoule per kg. All right, from 0 degree centigrade ice to 0 degree centigrade water. Now, the PCM, as I said, is used for melting or freezing, and we're actually using this phase change material or phase change concept in our daily life. For example, in a refrigerator, what is happening there? The evaporation or condensation is happening. So we know it that we are using is of almost everybody's house who are using this refrigerator. So now the melting point need to be in comfort range. For example, if we want to use this phase change material in our home, so is it the water does not good for us. You know why? Because the 0 degree centigrade temperature is not our comfort temperature. All right, so that means we can't use water as a phase change material for us, for our building insulation. All right, so how we can use this material? Because as I said, it changes the phase from solid to liquid or liquid to solid. So we can't keep it as a naked or like a open. All right, so we have to put somewhere in a containment, or we have to move, make some capsule using this material. Okay, so you can make like some pulses or cells or some shapes or balls in tanks. So this is the way is used. So to be effective PCM, it also needs the high diurnal temperature variation, as I said before, and also the temperature varies across the melting or freezing points. We have to have it, otherwise no use. So it should be like below or above this melting or freezing point. If we don't have that temperature variation, PCM has no use, because the height storage is the latent heat, and it must need to melt or freeze to get this heat. And it mostly rules out, for example, in coastal applications. So as you know that the temperature variation in the inland is much more than near the coastal area. So the coastal area temperature variation is not much. So that's why it's not very useful of using PCM in coastal region. All right, and also it is not very good for consistently too hot or too cold. For example, if it is too hot in the daytime, so your whole PCM will be melted, and after that temperature will increase. So that means instead of giving you comfort temperature, the temperature is changing and giving you the high temperature. So that is not good. So we have to think about it. What kind of PCM is It's good for you. It's good for your area. It's good for your building. So this is some real PCM people nowadays are using. It's called the bio PCM. So this bio PCM, as you can see, the latent heat is 150 kilojoule per kg. So this is much lower than the ice or the water. All right, but it's still okay. It's still good. The latent heat called bio PCM is still good. So if we prefer the comfort temperature is 20 degrees Celsius, so we can easily buy the bio PCM, which has the melting point of 23 degrees Celsius. And what we can make the find out some average about 2 or 3 degrees from the melting point. That is our comfort zone. We have to find out which zone is our comfort, and then we can find out the correct PCM for us. As I said before, if it is too far or if it is too low, it is not very good for our building. So this is, I can give you some example of PCM. So this is used in Australia, and it is, you can buy it from the market. And so this bio PCM is organic, the oil-based PCM, and it is encapsulated. You can see here, it's encapsulated in process in sheets, and the weight is about 2.7 kg per square meter, and it's a bit expensive, $110 per square meter. So it's a bit expensive. If we compare this one with the insulation cost, so it is about 10 times higher than the insulation cost. So the question is, then why we should use it? All right. So this is, there are some way we can explain, but people are doing a lot of research, and they are making how we can make it on a cheaper. So that's the way people are trying. And this patience and then the solution in here, it is an Australian company. So they are actually, this is actually US based. So they are importing from US, and that's why the unit is the US unit. We convert it. So the producer who developed this one, so they claim that it is 0.5 megajoule per meter square. So that is the amount they can store on square meter. All right. So, and this is the way you can do it. So this is actually very nice. You can directly use it just above your ceiling. So in house, you can just above your ceiling, you can directly just put it here. That's good. And also you can use it just on the wall. All right. So there are also some PCM you can use with the your ceiling material, but it is not available in Australia. So there is another one, just new PCM. So it's called Infinite R. The name is Infinite R. So it's made with a blended of clay or salt and water, the inorganic. So it is also similar encapsulation to BioPCM. Similar use case of BioPCM, you can use the similar way. And it is also available from this company in here. And they claim that it's almost double of heat storage capacity. And it is much cheaper. So you see, so people are doing a lot of research, and different companies they are developing some cheaper PCM. So this PCM actually not very available in Australia yet. So they start using this one. So the melting points of how can you find out? So if you know that that is it, the melting points you want for your application, either it's a building or anywhere. So once you select, okay, this is the melting point I want, this is the comfort temperature I want, then you can try to find that kind of PCM. So there are huge different types of PCM available in the market. So if you choose that this is the melting point PCM you want, they call it like RT35, RT50, RT25. So that is all the melting point. So you can specify that one and then you can buy from the market. So this is, you can see here the low melting point material, the organic material, and from 0 degree to 50 degree Celsius. All right, and this is above 50 degree melting point. Okay, and this is from 0 to 100, from more than 50 degree, from more than 50 degree to 150 degree Celsius. So that is the melting point. So it's a wide range of PCM materials are available. So you can use it as you need. So there are some inorganic PCM as well. So these are all the inorganic. So this is the below 50 degrees Celsius one. This is above 50 degree but below 200 degree, and this is above 200 degree and below 1000 degree Celsius temperature. Is all available. So there are some advantages and disadvantages of using organic, inorganic, or eutectics PCM. All right. So the organic PCM is, I say, just freeze without mass supercooling and subcooling. It's good, and is also ability to be incorporated directly. We can use, and it has good thermal performance, and is chemically stable and high heat of fission, and also is recyclable. So that is the benefit of organic PCM, but it has some disadvantages. It is low thermal conductivity in its solid state, and it actually very flammable, it burns very easily, and it has low density and a bit expensive. Okay, and the inorganic is high thermal productivity and is also large heat storage capacity. It's less expensive. It also is recyclable, but it has a high degree of supercooling. Okay, and lack of thermal stability. Okay, and is a corrosive and chemically instability. And eutectics is not very popular. It has a sharp melting temperature and high volumetric thermal storage density, but it has lack of currently available test data of thermophysical properties. It is not very available. So now, as I said, we can use a different way in the capsule, or you can put in a spherical shell. You can put inside. For example, you can put like the solid phase of PCM inside this one, and you can use it in anywhere you want. And when it's just heating, it's becoming liquid, and you can see, so it is not coming out from it. And when you change the temperature, cooling it becomes solid again. So the good thing is you can use it forever. It's neither destroyed nor nothing happening. Actually, it will be there. It's always change the phase. So this is a small video for using the PCM in the heat exchanger, flat plate heat exchanger. So I'm playing it. So these two are PCM. All right. Yes. So now, in terms of research, as you can see from this figure, the number of publications is recently increased dramatically. So you see in 1990 to 1995 or even 2000, has very low number of publications based on this PCM. But after that, it changed, and I have only data until 2017 or early 18, but recent data is more. So the researchers are getting interest of doing research on this topic. So this is the total picture, total summary of the classification of thermal energy storage material. So the thermal energy storage, we have like the physical storage and the chemical storage. So our aim is to talk about this one, not the chemical storage. So in this physical storage, as I already discussed about the sensible heat storage and also the latent heat storage. So the sensible heat storage, we have like a solid and also the liquid. So in the solid, we have like non-metals, we have metals, we have rocks, we have alloys. So all these things we can use for sensible heat storage. And the liquid one is molten salts, water, and thermal oils. All right. So one example I can give for the sensible heat storage, we normally do it at home. For example, if it is very cold someday, what we do is we just buy some bag of some special material inside, and that bag, small bag, we can put in the microwave. We can heat it, and then we can keep it, and we can go to the blanket at night, and that can give us the heat for a long time. It's about 1 or 2 hours. All right. So that is without changing the phase. We can store the heat from the microwave, and we can use for a couple of hours. So that is one example of sensible heat storage, but it is very for a short period of time. And the latent heat storage, that is actually what I was talking about, the phase change materials, and it can be from solid to gas, That is one example is the water. As I said, it has 3 steps, and you have a solid to liquid and the liquid to gas. So we use mostly this one, the solid to liquids. So solid to liquids, we have organic PCM, we have inorganic PCM, and we have this eutectic PCM. So these organic PCMs, we have like paraffins, we have fatty acids, we have esters, we have alcohols, all are organic. And the inorganic, we have salts and salt hydrates, metallic compounds, and metallic alloy. And so this one is not much easier. So now I'd like to talk about some application. So these are the application, our recent publication. We did with these precious materials, but we did not include all here. So it is very, very general. It's not directly applicable to any device or anywhere, just like a normal research. But after we published these papers, we got some call from BMW car company. So what they want is, they want to use this PCM technique to cool their hybrid car battery. Excuse me. As you know that the hybrid car, so the battery is charged when you are driving the car. So when you are driving the car, so the battery is charged. So for fast charging, what is happening is, so the battery quickly become hot. So if it is very hot, there is problem because engine is very close to the battery. So we need to cool down this battery cell, and also for the healthy, to keep the battery healthy. So we need to cool the battery cell. So the normal way they do is they use some fan, some coolant they use it. But when they saw our papers, they just thought maybe yeah, the PCM can be used for this one. And after that, we are doing some research on that. We are designing these things. How can we make the cell cool down? And we want to choose some correct PCM for the duration of the charging time. Otherwise, it's no use. So that is the way we are doing at this moment. A couple of my students are working on that project. So we talk about very quickly about the introduction of precious materials. I already talked a lot. And then the PCM's application, its advantages and some restrictions. And let us review about the PCMs in thermal storage system and the CFD modeling of PCMs and the multi-layer PCM. Sometimes we use not only one layer of PCM to get better performance. We can use multi-layer with different melting point. That sometimes is very useful in our application. So, so the PCM, as I said, PCM has got high melting and solidification heat capacity, and phase change process occurs at an almost constant temperature. Temperature doesn't change, and PCM can absorb or release a large amount of heat at a rather constant temperature, as we already discussed here. And PCM are very useful to create a constant temperature condition. So two forms of heat transfer we have. So these things I showed in different orientation. Before I put the temperature on the vertical line and the energy on the horizontal line. So that's why it looks a bit different. So you can see initially the temperature increase in the solid the PCM, And then when it reaches to the melting point, the temperature is constant, but it's gaining heat. Okay, so that is called the latent heat. And then when all the solid becomes liquid, then it starts again rising the temperature. And when it becomes the vaporization point, then it starts not changing the temperature until all the liquid PCM just die out from here. Alright, so it's a similar way but different orientation. So this is the sensible heat, as I said, with temperature change but without phase change, and latent heat without temperature change but phase change. And the important parameters we always consider is called the latent heat capacity. That means the amount of energy required to melt or to solidify. As I said, for water is 423 or something. So this parameter is very useful. And melting or solidification point, that is the most important thing. Which point, which temperature you need, and then choose the correct PCM. So the temperature in which PCM begins to melt or the solidify. So the latent heat has got higher storage density than sensible heat. As an example of RT28, so the melting point is 28 degrees Celsius. So the specific heat is 1900 joule per kg per Kelvin, and the melting heat is 245,000 joule or 245 kilojoule per kg. So as I said, the main function of PCM resulted from heat transmission at a constant temperature, that is the supply demand matching or peak shaving. So the supply demand matching means, for example, you are producing a lot of electricity, but some of them are not used. What do you want to do? So you can use the extra electricity supply for this PCM to store this energy. Sometimes what happens is, if it is like a very hot and sunny day, they produce huge solar energy, solar electricity. So that day maybe we don't need to use all of them the daytime. So we can use the extra one. We don't want to use it. So that we can say as a in the PCM. Right? So, and also the main drawbacks of PCM is, as I said, is very expensive and it changes the density. So that's why we need to encapsulate that one, and it's a low thermal conductivity. So just I want to give you just about three papers. We have a huge number of papers, but two of them is the numerical work and the last one is the experimental work. So the Farid and Kanjawa, they did the heat transfer rate. There is they find out the heat transfer rate between the PCMs filled in the tubular containers and the air which flowed across them, and the output is an increment in the system efficiency. They observe when the different PCMs with various melting temperatures applied. Okay, and Tian and Zhao, they also use numerical simulation, and they studied the porosity influences of the PCM. So they put a lot of pore with localizing metal foam in a container. So this pore actually helps on mixing, and that's why the heat transfer rate rose by using smaller porosities and bigger densities of porous medium, and using porous matrix actually eliminated the effects of natural convection because it's already it's mixing, so they eliminated the natural convection. And the Rathod and the co-authors, they showed the effects of longitudinal fins on the freezing and melting cycles of paraffin PCM. And their experimental study was carried out in vertical shell and tube heat exchanger, and they showed a large decrease in the solidification and melting time. That is what we needed. We need of up to 43.6% and 24.5% respectively when they apply the fin. So the CFD modeling, as you know that we need to solve the governing equations. I don't want to show it too much here because maybe most of you don't know about these equations. So this is we solve the continuity equation, and then we just solve the momentum equation for like a fluid flow, and then we solve the energy equations for heat transfer. So in this here, this energy equation, we have like the sensible enthalpy. This equation we solve, and the total enthalpy is this. And for liquid fraction during phase change process, it is defined by this. So I'm not going in details. So if you're interested, you can see some of my papers. So the multi-layer PCM. So what is the importance of multi-layer PCM? So this is the thermal conduction and mostly changing in different applications. So that's the reason we use multi-layer PCM. And then a PCM can only transmit the heat in latent form at its melting point, and other one doesn't do it. Okay? Only the one when it reaches to the melting point. And some thermal systems reach different temperature during their working period. And using the multi-layer PCM with various melting or solidification points provide the possibility of heat transfer in latent mode in a wide range of temperatures. All right. For example, if you use RT28 and RT50, so you can get a wide range of temperature variation. You can use. As I said before, there are some drawbacks of if the temperature difference is very high. So we can use this kind of technique. That's why we are doing this to overcome those drawbacks. So this is the multi-layer PCM solidification in a thin triplex tube considering natural convection. So this is the technique we applied. So this is the geometry. So you can see we have 3 layers. So inside is like a hollow. Maybe the fluid is going to this one. And we have one PCM is green. So one PCM, we have another PCM here. All right, so 2 PCMs here. So section A is the green one. And section B is the outer shell. And we use this fin and also the boundary. So we can use the aluminum containers or the aluminum shell we use it. So that is very highly thermally conductive. So we assume. So the assumptional boundary condition we use is the initial temperature is applied as 323.1 Kelvin, and in both PCMs, and they are completely melting. So we use the liquid one, and then the initial wall, the inner wall. So the inner wall is varied from 278 to 298 Kelvin. And the outer wall we put as the insulation. We don't want to keep like any heat released from here or the received heat from the outside. We just put it insulation outside. And the aim of this study was to effect employing the fins, how it works, and whether it helps or not, and the effects of employing 2-layer PCMs. and the effects of arrangements of PCM. So we arrange different way. Sometimes we put like the higher melting point inside and the lower and outside, and vice versa. And then solidification time for different models. So here we have like model 1, model 2, and model 3, different orientation. So we use like a plain fins for model 1 for 2 PCMs, RD35 and RD50. All right, so this is a plain fins. And in model 2, we use with more compartments and fins we use for the same PCMs. And model 3, we use the same as model 2, but with 2 kinds of PCM. So we in the model 3, we use 2 PCM, but up to model 2, we use single PCM. And we found that the solidification time for model 1 for RD35 is the maximum, 7,295 seconds. It took the solidification from liquid to solidification. All right, and we also see for model 2 and for 35 orientation A or and B. So in the B we got 5,457. So this is all different response time or the solidification time. So the liquid fraction of each PCM using model 2. So you know that model 2 is this one with more compartments and fins. For this RD35, we have A and B, and RD50 A and B. So we are putting the same PCM in both compartments. So layer 2 and layer 3. Just we can say the layer 1 is the middle, and the second layer and the third layer is A and B. So we put the same PCM in 2 layers, and for the same RD50 PCM for these 2 layers. All right, and then what we got. So we got the liquid fraction, as you can see from here. So this is the time, and this is a liquid fraction. So that means it becomes solid, solid, solid. Liquid fraction 1 means totally liquid, and then it starts solidification. So this dotted line is RD50. So RD50 is taking is becoming solid very quick, but RD35 is taking long time. So I need to go back, or I just Dr. Roy, can I finish it and then come back here, or I should explain it now?
Yes, so we have still time, so you can continue.
Yeah, just continue, and then I'll come back to the question later on.
Yes.
All right, thank you. So, so this is actually our claim. We did it here. You can see for RD35, the response, the solidification time is longer, and for this one is shorter. So that we found here. You can see for RD35, it takes long time for solidification, but for RD50, we got quicker. So this is for the other cases. I don't want to go very quickly. I don't want to show you very quickly here. So the liquid fraction of each PCM in each section during the solidification process for arrangement type 1, that is RD35 in section 1, and RD50 in section B. So these 2 different types of this one, and arrangement type 2, RD50 in section A, just opposite. Will be when we use the heat transfer, the temperature is 288 Kelvin, and for this kind of these cases. So you can see here. So this is the arrangement type 1. The 1 means is section A means the inside is your RD35 and outside one is 50. So this is the case, arrangement type 1, and arrangement type 2 is this, and then you can compare and you can see for arrangement type 1 we need long time for the solidification. Okay, so this is for the other case. If we make the opposite, we can see that for arrangement type 1 is the shorter, the short time we are getting the solid. It's come back to the solid for the liquid. Now the effects of different parameters on the discharging of double layer PCM to the porous channel, the second one. So we apply some porous channel. So here we use some the porous channel. So we define configuration. So this is the section A, the blue one, and the sky blue one is the section B. So this is the thickness is this called E, and this is called capital E. And then we see that effect of different parameters on the discharging of double layer PCM through the porous channel. And we assume that our assumption and the boundary conditions are we use the same PCM, RT35 and RT50 with some saturate in the porous matrix. And initial temperature we use 323.1 Kelvin. And again, we use the liquid one for both sections. And the inner wall temperature we varied from 278 K to 290 K, and the outer wall is insulated, and we use for the Rayleigh number 10⁶. So this Rayleigh number means that actually control your thermal intensity. So so it depends how your temperature difference or your the geometrical things. A lot of things depends on this RF value. This is their non-dimensional parameters. So that is called G beta del T H cube by kappa nu. So that means it depends on the material properties, it depends on the fluid properties, it depends on the length of the geometry and the temperature difference. So this all together, this is called the Rayleigh number. So the main aims of this study was to the effects of employing two layers of PCMs and their arrangements, and the effects of eccentricity of both sections. And as you can see, the effects of employing the PCM and the rearrangement, you can see the section A and the blue one and section B. You can see the section B is like this over time, but this one is having some fluctuation. All right. And for the other case, we have section A and section B. Section A responds very quick. Within 10 seconds, it's becoming solid. But for section B, it's taking long time to get this one. And for the other case, we have RT35 and RT50. If we use two different kind of PCM, then we can see for RT35, it's getting longer time to get solidification. Now, the effect of eccentricity of section A, you can find that if we vary from 0 to 0.75, we see the increase. It increased the solidification time when we increase the eccentricity. And also for the other case, when RT50 for section B, it is just the opposite. So when we increase the eccentricity, it is actually fluctuating. It's not we can say opposite, but it is fluctuating at the end actually. Is just happening the similar scenario. So for section B, we can see again, you can see some fluctuation here, but here is just very clear. For section B, RT50, we can see if the eccentricity is 0.75, we have the maximum time for solidification. Now, solid liquid phase change investigation through a double pipe heat exchanger dealing with time dependent boundary conditions. So use some time dependent boundary condition. We apply some diurnal temperature. That means the sinusoidal temperature variation we use for this case. So here we have like a section 1 and section A and section B. All right, and we apply this temperature. All right, so this temperature we applied some sinusoidal temperature, and we investigated these parameters. The minimum is 15 degrees, 15, and maximum is this, and these parameters we use, and we get at the end. We showed the assumptions and the boundary conditions. We use the RT35, but the other one is RT28. We selected initial temperature. We use the same 323.1 Kelvin, and the inner wall is actually oscillating boundary condition of the third kind, and the outer wall is constant third kind of boundary condition. And here we have again the Rayleigh number is 20%. And the main aims of this study is to show the effects of employing double layer PCMs and their arrangements, and the effect of amplitude and period of bulk temperature oscillation, and the effect of amplitude and the period of convection coefficient oscillation. So the effects of employing double layer 1, as you can see here. So the section A and section B, when we apply the time varying temperature, you can see the response. So the response for section A is very low response. Okay, it's not becoming solid. All right. So, but for section B, it's becoming solid here. But for section A, it's not. Its response time is not enough. The frequency used is not enough. So we need to give more time to get it up to here. It's not happening. So for other case, RT35 in section A and RT20 in section B, what is happening is now this section B is not responding. It's not coming always here. So it still is liquid more than 80%. Okay? The liquid is more than 80%. But for section A, it is actually becoming solid and keeping solid for some time, and then again become liquid. Okay, and then becoming like this way. So this is for other case. So the liquid fraction respect to time when both sections are filled with 28 RT28. So here is almost no response to section A, and for section B we have a little bit of a response, but it's more than 80% of liquid not becoming solid. But for RT35, we can see initially it's not good, but after later on we can power. But this one is section B is responding. Here is about 250 or 200, about 250 seconds is becoming solid and keep the solid. But for section A is oscillating. Okay. And amplitude, we apply the amplitude, a different amplitude is from 15K to 30K is applied, and you observe that the temperature, the liquid fraction response with time. Okay. So when the temperature difference is high or amplitude is very high, you can see the liquid fraction, the liquid from here to there, the range is very high. But when it's small, you can have like it's not becoming liquid, it's just coming back to solid. Okay. And this is for RT28 and this is for RT35. And periodic. Now we apply the period. We use 500 seconds, 1000 seconds. We use 1500 seconds and also 2000 seconds. We apply different period to see the response for liquid fraction RT35 and also for this RT28. Convection coefficient oscillation. So the liquid fraction, when you use the difference, the variation of convection coefficient from 50 to 200, we can see the response for solid and the liquid phase. and also for RT28, the response is not good, but for RT35, it gets good response. Now the period of convection coefficient oscillation, we put this one for RT35 for section A, and for RT28 for section B. So that's it. Thank you very much, Sukanto. I think I finished it earlier, right? No, almost. It's okay. I'll have a question answer time.
Yeah. So we have around 20 minutes.
Yes.
So we have received actually a few questions.
Now, what is the energy efficiency of using PCM as energy storage? How superior is it as compared to the other storage method? Yes. So as I said, the efficiency is very good. Efficiency is very good. As I said, you can just simultaneously going to use. The other form of storage is if you use battery, so you can use maybe later on, maybe a couple of days or maybe a month later on. But this one is you cannot store for a long time. But what I said is you can store during the daytime and changing the phase, storing the energy. But when at night time it releasing the heat, because the temperature is changing that time and releasing the heat. So you are getting almost the same the temperature if you compare at the like you are staying at home. So you are not feeling anything else. So in terms of this kind of storage, it is not storing for a long time. It's storing just changing the time, changing the temperature. Temperature is changing, but you are not feeling that. So that is the way is storing the energy. All right. So, but you cannot compare this on with the storage, for example, using battery or using some other form of things. So people are, I found that people are using, they are like using underground. They are making a very big reservoir, and during the daytime they are getting the solar energy and heating the water and putting this water inside the reservoir, and then at night time they can use pump to take the water, and so they can do that. So that is different thing. This is different.
Then we have a next question.
What is the question?
Why the liquid fraction may increase after a certain time in the model? Does this means heat transfer direction is changing?
Actually, this is for because we use two types of PCM. As I said, because maybe one PCM finished its melting point, it becomes solid, and then it goes to the other one. We reach the melting point. So that times it has some effect. That's the reason it is happening. Re-increase after certain time.
We got another question. Is that is there any PCM material available which directly absorbs solar heat and stored it?
Yes, that's what I showed you. The PCM material is available. You can use it. That's what I showed. Just let me show you that again here. Yeah, that is the PCM I showed you. So this PCM is available to buy. As I said, per square meter is $110. So you can buy it. Even I bought some for we want to do some experiment. That's why we bought some PCM. It is in my university. So, and I also showed how this PCM, this sheet is used in this building. So the top figure, this one, is all this bio PCM is here. So they use it here. So it is available. It is available to buy. And I also found that I think India is also maybe producing. I'm not sure, but this one is made in America. So we are in Australia. We are importing from America.
Okay. Anyone else having any questions, please, you can type in chat or you can directly ask also by unmuting your mic.
Yeah, so it's very hard. What is the name of the chemical name of RT35? I don't know. Sorry, I don't know the chemical name, but it names like RT35. RT35 means the melting point is 35 degrees Celsius. All right. So I don't know the name, but you can easily contact the company, and they can give you the details, or it is also available in the website. So if you search the Google in Google, so you can find this like RD35, maybe in organic or inorganic. So any kind of PCM, you can get all the properties. Because we need to get the properties when we did the simulation, we need to get all these properties. I did not put it here, but we have all these chemical and the mechanical properties we have. Otherwise, we cannot do the simulation.
Anyone else having any questions?
What is the opinion using PCM for other applications like solar focus and solar dryers? Solar dryers, solar focus. Just let me think. I don't think that you can use it for cooking, or maybe you can use it, but yeah, I don't think that you can use cooking, because your solar temperature is not like a maximum. We can get like a 41. So I know in India, in Delhi, temperature sometimes become 41 to 47 or 48 maybe sometimes, but that's not enough for cooking, and you cannot increase it using the PCM. PCM can actually absorb that, okay, and change this phase and keep this temperature. All right, so you can get maximum like your 48 or 47 melting point one. All right, so you cannot get more than that. So using this temperature in this heat, you cannot use for cooking. Okay, you cannot.
Okay. Any more questions? There is a question for me. This look like, will the recorded session be uploaded somewhere later? Yes, all the recorded sessions will be uploaded on the program website on the same day, evening or night time, and also the assessments will be uploaded there only, so you can attempt the assessments following the recorded session. Is there any more questions? Okay. I think we don't have any more questions. In that case, Dr. Saha, thank you very much for your very nice presentation. It was very
Thank you, Dr. Wan.
It was very informative.
Thank you for giving me the opportunity to present in this very nice workshop. And I hope the participants will get some benefit from this presentation. And if they follow my presentation, I hope they can answer the questions from the session you are going to do it in the afternoon, maybe after the all presentation. Thank you very much.
Thank you, Dr. Saha, for the nice presentation and very appreciation for our program. Now, let's conclude the session 1. Now we'll have a 30 minutes break, and the next session will start from 1:30 p.m. on Malaysian time. Please note that all the proceedings in the program website, all the time mentioned is as per Malaysian time.